Thank you. I was doing some system administration and lost track of time. Okay. So I'm going to start this up. Where's the button? There it is. Uh-oh. Oh. Bye, whoever you are. What? Oh, I'm sorry, I missed you. Visiting high school students. Bye. Oh, Lord. Oh, great. Okay. So, what we want to do is implement the stuff we did last week in plain old scheme. Okay? So, we want a system in which, well, in particular, we're worried about local state. So, we want a system sort of like this. We have a class, and we have an instance, and another instance, and another class, and it has instances too. And there are global variables accessible to everybody. There are class variables associated to any instance of, accessible, to any instance of that class. And then there are instance variables that each one has on its own. And we want to see how that works. How far did you get? You got nowhere. Okay. All right. Then we'll start up already. Okay. So the starting point is to notice that the substitution model that you've learned up to this point is not going to work once you can do set bang. Because if we take this 0 and substitute it in here, then the set bang isn't actually going to do any good. I'm sorry, if we substitute it in here in particular, the set bang, no matter what the set bang makes of that, this is going to just return 0 every single time. So we need a different model of evaluation that takes into account the possibility of changing the value of a variable and of a local variable and makes that possible. And I'm going to plug this in. Yes, I want to run it. Okay. Okay, so this is our first definition of a counter, like the count class that we saw last time. You would send it a next message and it would count up. And the way this works is that there's a global variable counter whose value is now 0. I can call, whoops, count, count, count. And every time I call count, it increases the value of that global variable. So this is just a straightforward use of setbang. And it shouldn't be a surprise to you that this works. But it's not good enough for that model that we want, in which we have private values of the counter, one for each instance of the class. So now, all right, this is the one that Jordy was writing. So here's an attempt to make a local value for each counter. There's still only one counter, but I'm making counter. I guess we have count and counter backwards. Instead of counter being a global variable, I'm going to make counter be local to this procedure. So that's the idea here. So now we're paying note, there is a global variable counter, which I can't get rid of. But forget about it, because we're not using it. So now, if I say count 1, I call count again, I still get 1. No matter how many times I call count, I'm going to get 1. Why is that? Well, every time we call count, it makes a brand new variable counter. And this is the use of let that we're accustomed to, where we create a variable just long enough to run the body of a procedure, and then that variable's gone. And the next time you call the procedure, it creates a brand new local variable. Well, that gives us local variables, but not persistent ones that we can use to remember the count from one call to the next. So here's the version that works. So first, let's load it. This has a different name, result, so we don't get confused with the counter global variable. Now if I say count, 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 you see that it does count, but result is not a global variable. It doesn't exist globally. And this works in a very strange way that isn't going to make any sense until we've been talking about it for a while. Namely, notice there's no parentheses around count here. So this is not a definition with an implicit lambda. The lambda that creates the count procedure is this one. And it comes inside the let that creates the variable which is going to be its local state variable. So that seems really weird. What does it mean to put a lambda inside a let? If you think of the procedure as just being the text of the lambda expression, which is how it worked in the Scheme 1 interpreter that you saw a few weeks ago. Remember when you said lambda, blah, 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 the value of that expression was just the lambda expression itself. And in that kind of world, because we were using the substitution model, in that kind of world, this doesn't make any sense, because it's how do you find the result variable that isn't defined inside that lambda? And what's new in the environment model of evaluation, which is what this week is about, is that a procedure isn't just the stuff in the lambda expression. It's the stuff in the lambda expression plus some way of finding free variables in the lambda expression. What's a free variable? It's one that isn't a formal parameter of the lambda. So it's not defined inside the lambda, it comes from outside the lambda. Now, up to now, outside the lambda just meant global. And that's how it is actually in a lot of programming languages. All those C-like languages, C, C++, Java, they don't have the idea of procedures inside procedures. So there's just procedure local variables and global variables, and that's it. But we have the idea of a lambda expression inside another lambda expression. And that's what you're seeing here, because remember, a let is an abbreviation for a lambda expression and then a call to that procedure. So this thing that's up on the screen is equivalent to lambda of result, and then lambda of nothing, set bang, blah, blah, blah. And call that with a 0 as its argument. Right? So the let means this. So in this lambda expression, the outer one, the green, no, I'm sorry, the outer one, the outer lambda expression, result is a formal parameter, so it's bound. So when you see a result in here, in this expression, it's bound. So we know what result means. It means this variable. But if you're only looking at the inner lambda, there's no way to know what result means if all you have is the lambda expression. So we're going to see later on, as we look at the details of the environment model, that a procedure is drawn like this. It has a left bubble and a right bubble. And the left bubble essentially points to the lambda expression. And the right bubble essentially points to bindings for the variables that are free in that lambda expression. So there's something here that says result equals 0. Okay, so both of these things are part of the procedure. And so when that procedure says set bang result plus 1, we know which result we mean, and we can turn that to a 1, and then next time turn it to a 2, and so on. Okay? So I know it isn't clear yet how we get here, but is it clear what we're trying to achieve? Right? That when you create that inner procedure, the one that's highlighted up there, it remembers where to find the value of result. Right? That's the goal. And if we can do that, then we can have different counters that each have their own result. So far, we don't. So far, we only have one counter, because we're working up to this a step at a time. But we want to see how this kind of expression turns into the count procedure, which is just that highlighted stuff, except knowing which version of result to use. So if we had a lot of these counters, if we said define count 2 and then the same thing, in fact, that might be worth doing. Never thought of that before. Let's define count 2 to be all this. Oops. Copy. Paste. Okay? So now we still have count, and it's now up to 4. We also have count 2 that's starting at 1. Here's the original count up to 5. Okay, so we have two counters, each of which has sort of the same code, but two different result variables. Right, because we did that let twice, one when defining count, and then again when defining count 2. Okay? If you're feeling iffy about this, it's not surprising. Stick with us. The problem is, oh, and I should have said right at the beginning, I apologize for the huge amount of reading in this week's assignment, which is the OOP below the line handout and 2.1 and 3.1 and 3.2. The reason for doing so much this week is I used to do them one at a time, and I've learned that students can't understand 3.1 until they've read 3.2, and they can't understand 3.2 until they've read 3.1. So there's a little bit of a problem here. And so what you're going to do, basically, if you haven't done it already, is read both sections twice. Okay? Read 3.1, read 3.2, then read 3.1 again, and it'll make more sense this time, and then read 3.2 again, and it'll really be clear. Okay? So we're cramming a lot into this week. 3.1 is the thing we're doing right now about what it is that we're trying to achieve. Namely, how can we get persistent local state variables? All right. Let me actually, I'm going to write that down. Persistent local state variables. Okay, you know what a variable is. You actually have heard the term state variable lots of times, starting with the iterative fast x. Remember that homework problem? They said you have to use an extra state variable to keep track of where the computation is up to. So it's sort of a memory of what we've done up to this point. So what's special is that we want two things that used to be contradictory. We want persistent and we want local. Global variables have always been persistent. You define it, it's there forever. Local variables until now, well, until last week, I guess, have always been kind of ephemeral. They come into being when you run a procedure and they disappear again as soon as that procedure finishes. So we want something that is like the best of both worlds. It has the sort of cleanliness advantage of locality, so that it's restricted to a particular piece of code, and the persistence of global variables. And we now see how to achieve that with the lambda inside the let, but what we don't yet know is how that works, how that manages to make a persistent local variable. And that's what we're going to see the rest of this week. Or you are without me. Okay. Now what we're going to do is we have how to make a single counter, and now we're going to look at how to implement essentially a class. So I have this thing, make count. Make count is sort of the equivalent to define class count, although it's much simpler than what a defined class turns into. So every time we call make count, it's going to make a counter. And notice that there are parentheses around make count, so the let that you see up at the top of the screen is part of the body of make count. It's inside the make count procedure. So it works like this. Define C1 to be, make count. Define C2 to be make count. And now I just call C1 okay, that's one counter. And now I can call C2. It starts from 1. Counts up. Now if I go back to C1, it'll say 5. Okay, so C1 and C2 are two counters. Make count is sort of a counter factory. And the way make count works is that every time you call make count, it does this thing about a lambda inside a let. So the value that make count returns is the value of this innermost lambda expression. So each counter is a procedure created by this lambda expression. But I can't any longer say, is this procedure? Because now we know that a procedure isn't just the information in the lambda expression, namely the formal parameters in the body, it's also what we're going to call an environment, meaning what are all the variables outside of this procedure to which this procedure has access. So how do we resolve free references, that is, references to variable names that aren't formal parameters of the lambda? And the answer is we look them up in the environment. And the environment gives us the value. Actually, technically, if you're a programming language person, I'm not supposed to say the environment contains the value. What I'm supposed to say is that the environment binds the name to a box, and you can change what's in the box as a 0 or a 1 or a 2 or whatever. But this is a level of complexity that we really don't worry about in this class. It's not going to matter because you're not trying to write a very efficient compiler for language. Okay, so that's make count. If I move up here and come down a bit, this is make count with all the lambdas made explicit. So this lambda comes from the fact that make count was in parentheses when I said define make count. So define with parentheses implies a lambda, and this one has no formal parameters because it was open parenthesis make count, and then there weren't any formal parameter names, just close parenthesis. This lambda comes from the let result be 0. Okay? So notice that this second lambda is the only one that has 2 open parentheses in front of it. Now, in talking about this, I don't want you to put in your head a sentence that starts, you have to use 2 open parentheses when blah, blah, blah. Okay? Instead, I would like you to understand what each of these parentheses delimits. So we just happen to be creating a lambda expression, this one. So this open parenthesis, the inner one, ends here. And that whole thing is a lambda expression. So it creates a procedure, namely the let procedure. Right? The outer lambda was make count. The second lambda is the let procedure. And then this open parenthesis goes with the inner lambda expression that I just showed you, and the 0 and this closed parenthesis. Okay? So the outer parenthesis right here, oops, this one, says call this function with the argument 0. Okay? And that's the let. A let is an abbreviation for 2 things, a lambda expression and an invocation of that procedure. So that's why there are 2 parentheses here, because the let abbreviates 2 steps. Make a procedure, invoke it. Okay? This inner lambda doesn't have 2 parentheses around it. It just has 1. And this is the value that the second procedure returns, and therefore it's the value that the first procedure returns. So this inner lambda is a particular counter. It's C1 or C2. It's this inner lambda, or a procedure generated by this inner lambda. Now, the way we get 2 different counters out of the same piece of code is C1 is this procedure, and C2 is this procedure, and they point to the same lambda expression but they have two different variables result. Two different environments, each of which has its own result variable. Okay? So, same procedure text, but different procedures with different persistent local state variables. Okay? Okay, moving on. All right, now we're at the point where we have to actually, yes, go ahead. You're talking about these parentheses? Okay, what goes here in a lambda expression is its formal parameters, the names of its arguments. So if you have open paren, closed paren, that means it's a procedure that doesn't take any arguments. Like down here, when I called C1, I didn't give it any arguments. Right? Does that answer the question? I'm not sure what you mean. When you say it returns, what it are you talking about? The lambda, every lambda returns a procedure. And every procedure has a formal parameter list and a body. The formal parameter list can have any number of formal parameters, including none. What's the purpose of using? The purpose of lambda is to create a procedure. We want to be able to invoke C1. Right? So down here, when I wrote this, what does this mean when you say that? It means, whoops, sorry, I clicked a button without meaning to. So what does that mean? No, I mean, what does it mean when you type to scheme, open parenthesis, C1, close parenthesis? What? Yeah, invoke C1. So C1 has to be a procedure, right? Where does that procedure come from? It comes from here. Now, why does it come from that one? Well, this outer one, that's the procedure make count. So the outer one actually includes everything all the way down to the end, like this. Okay, that's the procedure make count. I invoked that one at the beginning when I said define C1 to be the result of invoking make count. Okay? So that's why that first one isn't C1. This one isn't C1 because when you call make count, it doesn't just say return the value of this lambda expression. It says call this lambda expression with the argument 0 and then return whatever that returns. Okay? Well, so that's the let. So what does the let return? It returns the value of its body, which is this lambda expression. So this is the thing that we define C1 to be, is the value of this lambda expression. Okay? So the important new thing is that C1 isn't just this lambda expression. When you evaluate a lambda expression, you get one of these things with two bubbles, the first of which is essentially the lambda expression itself, the second of which is this other thing called an environment that we're going to talk about. Okay? Yes? What if you had the lambda result and you didn't have this lambda here? Then when you called make count, it would do all of this stuff. You don't want to do this when you call make count. You want to do this when you call C1. Right? Yeah. Yeah, good question. The question is, why is making a procedure coupled to making an environment? Actually, technically, you'll see that that's not the case. When we actually talk about how the model works, making an environment comes from calling a procedure. But the real answer to your question, which is a deep, good question, is that environments are not visible things in the language. Okay, it's not a data type with selectors like what's the value of this variable or anything. A scheme user does not see environments. In fact, we've been using environments all along, completely invisibly to us. So what we see is not environments. What we see is procedures. It didn't have to be that way. You could imagine designing a programming language the way you said. All I can tell you is 50 years of Lisp experience have shown us that this is a system that's really, really, really useful. Okay? So one of the things it lets us do is this business of making persistent local state variables. We get that free. And that's a thing, I think I said this last week, but I want to emphasize it again in the context of this week. All those other languages, they think that you need special object-oriented features in your language in order to do object-oriented programming. So there was C, and C wasn't object-oriented, so they made it C++, adding object-oriented syntax to the language so that you could define classes and things. We did the same thing last week. We made sort of Scheme++. But the point is you don't have to. That Scheme wasn't especially designed to be object-oriented. It was just designed to do the right thing, and object-orientedness happens to turn out to come out free when you do that. So if you talk to old Lisp hands about object-oriented programming, they all wave their hands and say, oh, objects are just closures. And what a closure is some way of representing which variable do you mean by this variable name in this place. And that's an environment. So all an object is, they're saying, is an environment. And that's true. All an object is an environment that contains instantiation variables, instance variables, class variables, methods, all that stuff have to be in the environment, and that's an object. Right? I don't actually offhand know of a language in which environments are actually user visible. Do you? Is there a language like that? Yeah. Recent versions of Scheme actually do have environments as a data type, but they only give you the global environment, and if you're lucky, no, not even if you're lucky. They give you the global environment and the even more global environment that has the initial values before you do any defines. Those are the only things that you get. You can't get any sort of local individual environments. And the reason for that, actually, has entirely reasons about compiler efficiency, or rather the efficiency of compiled code. If you keep the user's hands off the environments, then you can compile Scheme programs on the basis that the compiler knows, before the program is even run, what variables are in what environments, where to look for a particular variable, as seen in a particular context. So when you compile something like our count thing, and it says result in here, the compiled code doesn't say, look up the name result. It says, take the first variable of 2 environments back from here, or something like that. And that makes things much faster. Whereas if users can change environments on the fly, then the compiler can't make those assumptions, and the programs are a lot slower. So that's really why they do it this way. But it turns out to be good enough because we can use a procedure to represent an environment, and that's what let does, basically. Let says, I need to make an environment with this sort of local variable in it. And you could imagine having a make environment primitive that would do that and that would be used by let. But instead we just say make a procedure that has this local variable in it, and then call the procedure. And that's, you know, it's sort of two features for the price of one, in a way. Okay, but good question. All right, let me move on because we have hardly any time, entirely due to my stupidity in not watching the clock. But we're kind of in a rush, so let me move on. Okay, so we're going to talk about the environment model of evaluation. In the course reader, on page 320, you don't have to look at it now, but in there, is all on one page the complete rules for the environment model of evaluation. Okay, so that's sort of your reference document for how environments work. So let me remind you about the substitution model. What do we do when we see a procedure call? First step, recursively call eval to evaluate all the sub-expressions. The first one tells you what procedure we're calling, and the other ones tell you what the arguments are, right? So we always deal with actual argument values when we call the procedure, not actual argument expressions, because we've evaluated them. So that's what makes scheme an applicative order language. And that's still true in the environment model. Second step, apply the procedure to the argument list. Still true. The difference comes in what apply does. In the substitution model, so here's step 2a, it says substitute arguments for parameters in the body. Right? So we take the body of the procedure, which is an expression or a bunch of expressions, and we turn that into a new version of the body in which all the formal parameters have been replaced with values. So now we don't have any variables for the formal parameters anymore. And then eval the modified body. Okay? So that's the substitution model. Everybody clear about this? Questions? This you've known forever, since week 1. Okay, here's the difference. 2a. Make an environment with the parameters bound to the arguments. Bound to means like pointing to, having that value. Okay, so we make this new kind of thing called an environment, and then 2b says eval the body. Not some different version of the body, but just the body in the new environment. So what is eval in all about? Well, substitution model, we say eval an expression. In the environment model, we say eval an expression in an environment. Okay, so in the real scheme interpreter, eval takes two arguments, not just one. And the second argument is an environment in which all the variables have values. Okay? And we look up variables in the environment to find out what their value is, and we also look them up in order to change the value if you do a set bang. Okay. So that means, for example, that we have to change the read eval print loop so that when you type in an expression, it says eval read, right? Call to read. So this is the expression that you typed in. And in the substitution model, there'd just be a closed parenthesis here, but instead we have the global environment. This is not a variable that users of scheme see. This is a variable in the scheme implementation itself. So if you read the code for the Chapter 4 scheme evaluator, which comes up in a month, it looks like this. So there's a variable called the global env. But we're going to add to that, and here's the other crucial point. Because when we make a new environment, there's two steps. One step is to make a box, which is called a frame, in which we have something like result equals 0. So that's a frame. And this frame has a pointer to some existing environment, like, let's say, the global environment. Okay? Does that picture start to look like that picture a little bit? Okay, Wednesday and Friday, you're going to see how this model, which is really very simple, fits on a page, gives us that picture in effect. Okay, I will see you in a week, but don't skip lecture on that account. It'll be important.